Hi everyone, my name is Ryan.
Hi, my name is Rachel.
And my name is Madeline, and we are part of the SRC program under the astrophysics cohort. Our mentor is Ruby Byrne, and for the past 6 weeks, we have been talking about atmospheric or studying atmospheric analysis using overall LWA data. The main focus of our research has been to characterize the ionosphere over space and time. To do this, we learned more about radio astronomy and the overall LWA telescope. We practiced reading and interpreting scientific papers about the topic, and most of all, we developed skills in Python and using this to analyze data.
So what is radio astronomy? Radio astronomy studies the universe using radio waves emitted by objects such as galaxies, supernova remnants, and the sun. These objects appear as radio sources and measurable positions of the sky. Although radio waves are visible to the human eye, they are still part of the same electromagnetic spectrum that us humans see. Because they're longer they're simply just longer wavelengths and lower frequencies. Radio waves are important because they can travel through clouds or dust that block visible light.
An important part of radio astronomy is 21 centimeter cosmology. Most of the atoms in the universe are hydrogen, which emits light at a wavelength of exactly 21 centimeters. However, as the universe expands, light gets stretched into longer and longer wavelengths, which gets stretched into the radio spectrum, which we can measure on Earth. However, the ionosphere interferes with that data that we get from ground-based telescopes, so we'll be getting more into that soon.
Our research was specific to the ionosphere, which is a layer of the Earth's atmosphere that contains a high concentration of ions and free electrons that extends about 50 to 600 miles above the Earth's surface. What makes this interesting to study is that it has a tendency to distort incoming radio waves, making sources in the sky appear shifted from their true positions when conducting a low-frequency radio astronomy.
On Earth, we can see the light from galaxies, supernovas, and stars by using telescopes. Throughout the rest of the presentation, we may refer to these as radio sources. Sources appear in different positions than they actually are because the light is bent due to variations in the atmosphere across space. You can see that in the diagram, and it's kind of like how objects appear bent or shifted when you look at them through water. We can measure this offset to learn more about the density and structure of the atmosphere.
The OBRO. The OBRO is a low-frequency radio telescope located in the Caltech Owens Valley. The OBRO LWA is different from what you imagine a telescope to be because radio waves have such long wavelengths. Radio telescopes need to be much larger to have a comparable results to optical telescopes. The OBRO, rather than trying to build a single dish miles wide, is made up of 352 antennas that work together as a single instrument. The longest baseline or diameter of the array is 2.4 kilometers.
So this is one of the things we looked at. In the first week, we basically did research about the overall ionosphere, getting more familiar with the literature and what research has been done so far. So this is one of the papers we really looked at more closely. It's by Jordan et al. In 2017. And they're analyzing the atmosphere using the Murchison-Whitefield array, which is in Australia. It's at a higher frequency than what we were looking at. It's about 200 megahertz, but they found and characterized structures in the ionosphere, which you can see in type 2 and type 4 on the right side. And basically, if you look at these graphs, the arrows, which are pretty small, but you can probably see them, those represent the offsets of the sources or how far away they appear from where you expect them to be. And then the background represents the derived structure of the ionosphere or the density of electrons in the ionosphere.
This is a sample image of the data you're looking at. This is a snapshot of around an hour long. We found over 6,000 different sources. This image is facing up. It's a circular image, and because it's a horizon snapshot of the entire visible sky. These sources could be galaxies or stars or supernovas.
Using PyBDSF, which is a Python package that serves as a blob detector or source finder, we were able to take images from the telescope and identify how many sources were detected in each image. In this example, I specifically looked at images from the 18 megahertz batch. On the left, you can see the first initial snapshot that was taken on May 7, 2025, and this represents 10 seconds of data. And on the right is a deep integration image which covers the sky on the same day However, it covers over several hours of data. It can be seen that more sources were picked up in the deep integration image, which was helpful for us to understand as we moved forward with our research.
One of the first things we did was sorting through the data to determine whether it's good or bad. We used 3 variables to determine that. Peak, which is how bright the source is, RMS, which is how much the background noise is, and SNR, which is how clearly the source stands of the noise. If the SNR passes a certain threshold, it's labeled as good. In our test, we had high SNR values, so luckily all our sources were good, but we need to do this because bad sources can cause phase shifts to make it possible for us to mislabel the atmospheric shift that's due to bad data.
Right ascension and declination are the units of the celestial coordinate system used by astronomers to map out the sky. These will serve as the x and y axes for the majority of the maps that you can see for the rest of our presentation. Even though both of the previous images shown before of the 18 megahertz initial snapshot and deep integration observations depicted the same night of data, the sources appear to be shifted. So the next step of our research was to understand the positional offset that the ionosphere caused over time. As seen on the scatter plot on the left, the deep integration image detected a lot more sources, around 494, while the initial observation only found 229. You can see that there are several points where the sources overlap with one another, which means that these sources are most likely the same. After running an algorithm, I matched these source pairs, which provides a better understanding for where these astronomical sources are actually located in the sky. As seen on the table, at least for the 18 megahertz images, the positional offset caused by the ionosphere ranged from around 1.18 to 10 arc minutes. To visualize the positional offsets, I mapped out the sources on a scatter plot, which appear to be overlapping. Then I added vector arrows, which represent the offset between the 2 images of each source. They are scaled up so we can see how they vary. The arrow links represent the magnitude, while the color represents the direction. For the 18 megahertz image batch, we were provided approximately 350 snapshots of data, all of which last for 10 seconds. To see how the offsets varied over time, I made an animation that has the deep integration source locations as the reference points, which you can see as the white to gray dots. Then I ran an algorithm, the same algorithm as before, which calculated the positional offset of sources between images to map out the offsets of every source for every snapshot, where each grain is a new snapshot. These values varied depending on the frequencies we were looking at, and in this case, lower frequencies resulted in higher offsets or greater offsets.
So once we extracted those sources, we needed to set constraints to try to remove these errors. So several of my sources, when I put it on the histogram, turned out to be below the horizon, which the telescope should not be able to see. So we limited these out and we set it so that they have to be at least 5 degrees above the horizon to be considered. Another point is the brightness of the sources. If they're really dim, they're more prone to errors. So we limited the minimum brightness of the source to 1 JSP per beam, which is an astronomical unit of brightness. And then for matching, I wanted everything to be close to each other, like sources to be close to each other to be considered a match. So I set the limit to 5 arc minutes, which is about 1/12 of a degree. And I wanted to match with flux, but unfortunately that was not possible because the different images that we used to try to match between were processed differently and had different flux scales.
After calculating the positional offset at specific points, our next objective was to estimate the offsets at every pixel in the overall LWA images. This was done through a process of interpolation, which is the process of estimating an unknown value that lies in between 2 known values. These are maps of the estimated positional offsets of every point in the sky that were calculated using the offsets of the initial snapshot and the deep integration images as shown before. Each point on the map represents how much a potential source at that location would be shifted by the ionosphere. The map on the left focuses on the RA offset, and the map on the right for the depth offset, also known as right ascension and declination. Using the Pythagorean theorem, I was able to calculate and map out the overall magnitude of the offsets. This helps develop a better understanding of the ionosphere because it has a spatially varying electron density, meaning that the positional offset is not going to be the same across the entire sky.
To explain, TEC means total electron count. It tells us how many free electrons are in the atmosphere. STC is the slant total electron count. That means the total electron count on the angle path from a radio source to a telescope. VTC means total electron count, vertical total electron count. This is electron count straight above one location. We use STC because the OBRO, LWA, usually looks at sources from an angle. This equation shows differential TEC causes an apparent source offset. The larger the differences in STEC or STC produces larger offsets, especially at lower frequencies.
Using the same 18 megahertz data and the calculated positional offsets from before, I was now able to calculate the S-TEC. Each point on the map represents how rapidly the S-TEC changes across a physical distance in the ionosphere. This represents the spatial gradient of the S-TEC measured as the change in TEC units per meter. Because radio source positions are proportional to the S-TEC gradient, regions with steeper gradients resulted in a greater positional offset.
We convert S-TEC to V-TEC so we can compare all sources fairly. S-TEC depends on the angle where we look at sources. We look through the sources of the ionosphere. Lower sources pass through the ionosphere more just because of geometry, as you can see in the image. And using the Minucci et al. 1993, we correct for that angle and estimate the vertical TEC.
And then once we had that vertical TEC, it was actually a differential vertical TEC because it was still the derivative. It was not actually the full ionosphere, because again, our telescope only measures changes in the atmosphere. It's not actually measured the ionosphere itself, because we're only measuring the offsets. So we had to convert these back into to reconstruct the ionosphere, which you can see we did a synthetic test on the screen right now. So on the left side, the arrows represent the offsets, or basically how much it's changing at a given point in space. And on the right side, the background is the reconstructed ionosphere, which you can see the middle is actually the tallest point and the outsides are more like flat because we used an algorithm to basically convert the derivative into back to integrate it again. And then another thing we looked at was global atmospheric map models, which basically modeled the atmosphere around the entire world. So we basically looked at these data sets that had lots of points around the world, but they were pretty coarse data. They were only about 2.5 degrees of latitude and 5 degrees of longitude around the whole world. So this does not actually give us specific ionospheric values for every point in the sky, but we were able to give a baseline for how much ionospheric activity there was at a given time. And then another thing you can see on this map here is that during the daytime, there's a lot more ionospheric activity, and at nighttime, there's less because during the daytime, the sun's energy actually excites the ionosphere and gives it more energy.
This is a graph showing the ionosphere around the OBRO. Each dot is one point from the satellite map. The brighter the color, the more electrons. This is to point out how the satellite data is good for seeing the overall structure. But because the grid is very coarse, each point covers an large area, it's not so good. It's not as good as the OBRO for getting very specific data. So the satellite data could tell us the general background about the TEC, but it could not explain the detailed source by source distortion we saw in the OBRO images.
So this is an example of one of our final products. From over an hour of imaging on May 7th, 2025. This is at 64 megahertz, which is a higher frequency than what Madeline talked about earlier. And that means the ionosphere has slightly less impact on the light passing through, and we're able to pick up more radio sources overall. Each frame of this animation is about a 10-second image of the sky looking straight up. And the arrows again represent the source offsets, or how much the sources appear to have moved. And the color represents the direction, with 0 being straight to the right and going counterclockwise, like a unit circle. The background represents the reconstructed total electron content of the ionosphere in that part of the sky. And then this is our results across different frequencies. All these plots represent the same 10-second snapshot of the sky. This was on May 7th, 2025 at a local time of 2:51 a.m. It is at the OBRO LWA array. Overall, we can see that there are similar structures identified across different frequencies as we expected. But there are overall longer arrows on the left side because there's more ionospheric refraction at lower frequencies. And then on the right side, the arrows almost disappear because they're very, very small. The offsets were much less at higher frequencies. And then also you can see that on the very left side, we had less sources. So we were able to get a less, lower quality, reconstruction of the ionosphere versus in the middle plots. We had a lot more sources and we're able to get a much higher quality image.
In conclusion, if we were to continue our research, the next steps we would take are looking at more data besides the couple of days that we studied, as well as other frequencies. We would also compare atmospheric structures across frequencies, finish our implementation of data from global atmospheric maps, and fine-tune our constraints to reduce the probability of errors in our research. For Caltech radio astronomy, some possible steps are developing new instrumentation, such as the DSA and the lunar radio array, that are capable of doing further measurements. Also, having radio telescopes in space would be more beneficial for this research because they wouldn't be affected by the ionosphere's effects, making it easier to analyze source positions and other information that is relative to low frequency astronomy. Thank you.
Have some questions?
Yes, so when deciding whether each snapshot of data was good or bad, did you only use signal to noise ratio to decide that?
Yeah, that was it. Well, I initially used the algorithm and it just hand reviewed like 20 of them or so myself and then saw they were all good. And then he also, I showed my algorithm results, but he also did his own and he also got them all back as good. So we decided it was good enough to use them all.
And then also just a quick visual check is we showed the plot earlier. Where you can see the image of the whole sky, and then we can just visually check. Sometimes there are calibration errors or processing errors, so just I don't know, it's pretty far back, but we could print out an image like this and then just look at it to make sure that it looks like reasonably good.
Could you just say again, what changes when you go from the initial observation to the deep integration that allows you to pick up more?
The deep integration image covered like the sky over several hours rather than the initial observation was over 10 seconds. And also I'm pretty sure that the deep integration was the data collected was just better quality images taken during that time, so I was able to pick up on.
Natalie, I think you said you created the animations. Was that a new skill for you, or what did you use to build them?
We had used Python for that. It was very new because I don't really have too much experience in coding. So through that it was a learning process being able to take Python skills and translate that to like visualizing the ionosphere, which I had never learned about ionosphere before either. I didn't know what that was. So I think it was really interesting, like throughout the entirety of the program, to be able to not only use code, because you could run code, but then it's just like you're an exercise and you see a result, but you don't know how that actually relates to real life. So being able to make something as an animation or something as interesting as an animation for the purpose of this project was new, but it was exciting.
Any other skills any of you learned that you didn't have when you started?
There was a lot of I forgot to say here, but when we talked about the packages, a lot of these packages I haven't used before, they're specific for astronomy, such as AstroPy or IPSF, which I had never heard of.
And then for me, I also did a lot of programming before, but I was getting more used to Python and data analysis throughout this process.
Do any of you see a career in astronomy?
Maybe. I think I have to do more before I actually decide. I have a lot of time to, so I'm not interested.
I'm not sure about astronomy specifically, but I did think it's really interesting. However, I am pretty set on focusing on physics in my career. So if I do find that I specialize in astronomy, then it would be nice, or it is nice that I had a previous experience. So possibly.
I'm still not sure yet.
More questions? Thank you.